Hello, everyone. Today, I'd like to talk about how the cognitive mechanisms of habituation and dishabituation in animals can be applied to ACI, animal-computer interaction. Start with a question. How do animals respond to new stimuli? And why do they seem to lose interest over time? Animals don't passively accept everything in their environment. They constantly evaluate whether a stimulus is worth paying attention to or can be ignored. This evaluation is guided by key cognitive processes: habituation, which is a gradual decrease in response to repeated stimuli, and dishabituation, where a renewed response occurs when something new appears. Today, in the emerging field of ACI, animal-computer interaction, these mechanisms are actively used as core design elements. ACI refers to a research field that seeks to enhance animal welfare by designing systems in which animals can autonomously interact with digital technologies. These systems aim to provide cognitive and sensory enrichment and facilitate intra- and interspecies interaction. In this talk, we'll look at how habituation and dishabituation shape ACI design. So, what are habituation and dishabituation? Habituation is a gradual decline in response to repeated stimuli, like an animal that's startled by a noise at first but eventually stops reacting. Dishabituation occurs when a new stimulus restores the response, indicating that the animal is not simply tuning out, but cognitively detecting changes and adapting. Together, these mechanisms help explain how animals focus on change and filter out irrelevant information. These mechanisms are also widely used in comparative cognition research. A well-known example is the novel object recognition test, where an animal is first shown two identical objects, and later one is replaced with a new one. If the animal spends more time exploring the novel object, it suggests memory and cognitive discrimination, not just instinct. This makes habituation and dishabituation valuable tools for studying attention, memory, and exploration. How can these concepts inform ACI design? Rather than offering repetitive stimuli, ACI systems are designed to vary the form, timing, and delivery of interaction to prevent boredom. For instance, stimuli may be removed and reintroduced, or animals may be given control over when and how they engage, promoting novelty and autonomy. In this sense, ACI technologies act not just as tools, but as cognitively informed design systems. Let's explore how this strategy is applied in practice. Let's look at three case studies from the 2021 ACI paper by Hersky J. Douglas and Weber. First, the KWO system, connecting with orangutans. It allowed orangutans to interact with projected visuals using their hands or feet. At first, they engaged actively, but interest gradually declined, showing habituation. Later, in some cases, their engagement returned, indicating dishabituation. This shows the need for ongoing observation and well-timed changes to keep animals engaged. Next is the second case, doggy vision. In this system, videos played automatically when a dog approached the screen. Some dogs lost interest quickly, while others stayed engaged longer. This shows the importance of personalized design that accounts for individual differences. Third case is the Saki tunnel. Here, Saki monkeys encountered different visual scenes, like forests, insects, or underwater environments, each time they entered the tunnel. These scenes were changed weekly, which helped maintain their interest over time. Together, these cases highlight one key idea. Animals are not passive users of technology. Designs that ignore their cognitive rhythms will quickly lose their attention. Outside of research, real-world applications also utilize these principles in enrichment strategies. In an experiment at SeaWorld Orlando, dolphins and marine mammals showed longer engagement when stimuli were provided at irregular intervals compared to fixed schedules. This demonstrates that how stimuli are delivered, rather than how often, plays a key role in preventing habituation. In addition, Taru and Bashaw, in 2007, proposed a few key design principles that are highly relevant to ACI. First, if a stimulus is too similar to the animal's environment, habituation happens quickly. Second, strong and intermittent stimuli slow down that habituation process. And third, when stimuli are designed to be unpredictable, animals tend to stay engaged for longer. These insights can be directly applied when designing ACI systems to keep animals attentive and interested. In conclusion, habituation and dishabituation are more than behavioral patterns. They're key to understanding animal cognition and applying it to design. ACI is moving beyond screens and buttons toward cognitive interfaces that support ongoing animal engagement. At the heart of this shift is a simple but powerful idea. Notice when animals lose interest and help them regain it. In this way, ACI technology becomes not just a tool, but a way to understand the animal mind. I hope this presentation has offered a small insight into the question: how should we think when designing technologies to engage with animals? Thank you.